So last time we talked about the one-dimensional Newton's method and other open domain methods such as the secant method. We also talked about the fixed point iteration. And today I want to extend the treatment of Newton's method to talk about multidimensional problems. These are problems that have more than one equation and more than one unknown. So to begin with, let's consider the following two equations. We have a function g of x comma y equals 0 and f of x comma y equals 0. And each of these two functions is a surface in 3D. So instead of having a y-axis and an x-axis, now we'll have an x, y, and z-axis, where we'll assume that the z-axis is the value of the function. So these are 3 dimensions, and now that we have two functions, two surfaces when they intersect are going to intersect in a line, and we can visualize this as shown in the following plot. Here's a visualization of both the F surface and the G surface, and you can see where they intersect happens along this black line here. Now the solution is going to be where these lines intersect each other and where they intersect 0, because that's what we're solving for, is where they intersect 0. And so that'll be the solution of our problem. And so the surfaces intersect in a line, and then the line intersects the plane at particular points, and we can have more than one solution. And of course, we usually don't know about what the shape of the function is or what the solutions are. Now, you could, instead of considering the picture as shown, you could also imagine that the function itself, each individual function, f and g separately, intersect with the z equals 0 plane. That is, we want to know where the surface f intersects with the plane 0, and that'll do so in a curve. And then the g surface will also intersect with the z equals 0 plane in a curve. And then those two curves where they intersect will be equal to the solution points. So this, you can see right away, is going to be more complicated than the one-dimensional situation with f of x equals 0 for a couple of reasons. One is just in terms of trying to keep track of more than one variable, and the other will be that graphing it is usually out of the question when we're dealing with more than two unknowns. Many of the methods that work really well for 1D don't work very well at all when you try to extend them to multidimensional problems. The Newton's method is particularly easy to extend, and so that's the method that we'll talk about in this discussion. So, with Newton's method, remember our motto: if you can't solve your problem, solve an easier problem. In one dimension, we made an initial guess, and then we approximated the function as being linear around the guess, and then we solved the linear problem, which gave us an updated solution that we can use as a guess, and then we repeat. To find the formula for that line, we just used a truncated Taylor series representation of the function f of x about point x0, so that's given here. F of x is approximately equal to f of x0 plus the derivative evaluated at x0 times the displacement from that point, x minus x0. And you can see that here in this graph. So if we have a function e given by this blue line, then we would evaluate, say, some initial guess, 2.5. We evaluate the function, and then we approximate a straight line to the function. That would give us a new guess, and we iterate on that, attempting to find a solution if there is one. We're going to do the same kind of thing in 2 dimensions. We make an initial guess for both x and y, and then we approximate the two functions, f of xy and g of xy, as tangent planes at the guess points. So to do this, we're going to find the intersection of the tangent planes with the y equals 0 plane. And solving for these is going to be a linear problem, which is much easier to solve than the nonlinear problem. Just like in the one-dimensional Newton's problem, solving for the straight line approximation was an easy thing to do. We can do that directly. So what we're doing is we're going to find the intersection of the tangent planes with the y equals 0 plane, and then the intersection of those tangent planes will be a line, and the location of the intersection of that line with the y equals 0 plane will be the solution. So a line intersects a plane at a given point. So the multidimensional Newton's method looks like follows. We approximate each function as a Taylor series. So f of xy is equal to f of xy evaluated at the guess point, x0 and y0. And then we've got a displacement from that initial point written in terms of the slope of the function in x times the displacement in x plus the slope of the function in y times the displacement in y. And then we do the same thing for g of x. G of x comma y is approximately equal to, when we keep only the linear terms, g of x, g evaluated at x0 and y0 plus the slope in the x direction times the x displacement plus the slope in the y direction times the y displacement. So here delta x is just shorthand for x minus x0, and we do the same kind of thing for y. Now, on the left side of the equation, by definition, we're trying to find where the solutions, where these functions cross 0. So we're going to set f and g equal to 0. So I'll have zeros here. And we can write this in matrix form. So we can recognize this if we just put parentheses around it. We call that a vector of function values. The first would be f and the second would be g. And then that's going to be equal to this vector. F is the first element and g is the second. Plus, in this case, we'll have a matrix times another vector. So the matrix will have elements df dx, df dy, dg dx, and dg dy, and then the vector will be dx and dy. So in matrix form, you can see that here, 0, 0, f, g, and then the matrix of coefficients times dx and dy. And so these elements can have a one-to-one correspondence between these two equations. So we can, where we're using vectors here, we can, rather than show the individual components, we can use the shorthand notation, and we can rearrange this. We can call this vector f, which is a function of vector y, or vector x, rather. So we will call this matrix J, which is the Jacobian matrix. It's the matrix of partial derivatives multiplied by the vector of displacements. So here we have, if we if we pull this vector to the other side, then we have J delta x equals minus f of x. Now this extends, I've written this here for 2 dimensions, but it extends trivially to any given number of dimensions. So if we had 3 equations and 3 unknowns, we'd have f, g, h of x, y, z, and then you'd have a 3 by 3 matrix, df, dx, df, dy, df, dz, dg, dx, dg, dy, dg, dz, and then delta x, delta y, delta z. Here I'm using bold symbols to denote vector quantities. Now for multidimensional problems, it's kind of inconvenient to use f, g, h, and x, y, z. You run out of symbols too quickly, so we'll just denote these as function 1, function 2, function 3, and variable 1, variable 2, variable 3. And so our goal here is to find our new updated x value, and that's built into this definition for j. So we had dx, if we look at the first bullet point, we had dx is x minus x0. So if we have dx, then we can solve for the new x. X would be equal to x0 plus dx. So what we need to do is find dx. And we can do that from this equation, j delta x equals minus f of x. We can solve that for dx. And that ends up looking like a linear algebra problem. We just have delta x equals minus j inverse multiplied by f of x vector. Now, it's important to note the structure of this J matrix. In general, the row I and column J of this J matrix is the partial derivative of Fi with respect to variable xj. So they go in order. Jij is dFi dxj. Now, J can be expensive to compute when we get large systems, so this is kind of an A-side. It's often reused for a certain number of Newton iterations and updated when it gets out of date. But those are the kinds of things that we'll keep in mind as we move forward. And then again, once we have the dx vector, we can solve for our new. X new is just x old plus dx. So this is kind of nice. It's another example of how numerical methods very often reduce to solving a system of linear equations, and that's exactly what we have here. In the one-dimensional Newton's method, if we could just go back here, we had that f of x was this f0 plus f prime times this slope quantity, and then if we want to solve for the dx, then we would take, and then we set f as 0, so if we wanted to solve for this dx, we would go f minus f divided by f prime, and that would give us that delta, which we then find x by going the delta plus x0. So we're doing essentially the same kind of operation here in multi-dimensions when we solve for dx is just j to the minus 1 f. So instead of going f of x divided by f prime, now we have to do a matrix inversion and a multiplication by the vector. So let's talk a little bit about how we go about implementing this. In 1D, we needed 3 functions. The first was the Newton's routine that does the Newton steps, so that one's kind of obvious. And then that needed to operate on a function for f of x. And then we also needed another function that defined the derivative, df dx. So when we do a multi-dimensional case, it's going to be virtually the same thing. We're going to have another Newton method, and it's going to do the Newton steps. It's going to perform the inversion, the solve here for delta x equals negative inverse of J matrix times the f vector. And then it's going to compute x from dx, and it's going to perform the convergence checks, etc. So that's the Newton routine. It basically does the same thing as the other one, the 1D one. And then our second is going to be a function that rather than just have an f of x where we pass in a scalar and return a vector, now we're going to pass in the vector of unknowns, and we're going to return the vector of function values at those unknowns. So functionally, the only thing that's really changed here is that we've made the symbols bold. So when we implement this in languages like Python or MATLAB, they're going to look very similar between the 1D case and the multidimensional case. And then finally, we need a function that takes x. We pass in the x vector, and ideally we also pass in the function too, if needed, and it returns the Jacobian matrix J. So let's review then. Last time we gave an example in Python of the one-dimensional Newton's method, and this was the code for it, a very simple version of the code. We've called it Newton 1D, and it's got x. We pass in the initial guess, x0, and then here I've added here I've added a couple arguments where we're passing in the function to evaluate and the derivative of the function. So these are two functions, Python functions that we're going to pass in. And then we tell it the convergence tolerance and give it a maximum number of iterations. And here it has a default value of 100, so if you don't pass in that argument, it'll just assume to do 100. And then the loop, we iterate over all the iterations. We iterate from 0 up to 1 minus the maximum number of iterations. And then we perform the Newton steps. So this will be the x new equals x old minus f of x old divided by df dx old. So we're evaluating the function and we're evaluating the derivative. And these are the two functions that we passed in through the function interface. And then we do a convergence check. So we say if the absolute value of x new minus x old is less than the tolerance, then we're going to return the solution and the number of iterations it took. So this is just saying if you're not changing, then you can call yourself done. And you can make more complicated convergence criteria if you like relative errors, for instance. And then finally, after the error check, we need to reset our values. So we've just taken a new step. So we need to say our old value is now our x new value, and then we're going to start over. And we just converge that, and it returns if it hits the tolerance, and if it doesn't, if it reaches the maximum number of iterations, then we print a warning, and we return the current solution value. Let's see if I can get this thing to go. Okay, here we go. So let's look at the multidimensional Newton's method. In this case, we have effectively the same code. The single line for x new is now replaced with these three lines, where I'm computing the f vector by calling f of x0, and I'm computing the Jacobian by calling the Jacobian function. So they look very similar. Instead of f and df, we just call the function, and we're just passing, in this case, the vector x0, and it returns f of x. And we pass in x0 to the Jacobian function, and it returns the matrix J. So it's very similar. And then our update is x new equals x old minus the matrix analog of f vector divided by f prime, which in this case was the inversion. We need to solve the linear system J and f vec. So this is like this will be solving for j minus 1 times f vec is what this is, this last term. When we add that to x0, so this whole quantity here basically represents dx, this negative np.lineage.solve j comma f vec. That's basically the dx vector. So when we add that to x0, we get our x new. So that one line right there. And then we do the same kind of convergence check, but this time because we have a vector, we don't want to just do x new minus x old as a scalar. So we're going to look at the norm, and so here I do np.lineage.norm of it, and then I take the square root just to get something more like a length in the vector sense. Check whether it's less than the tolerance, and if it is, then we return x new and the number of iterations. So, and then x0 equals x old. So with languages like Python or MATLAB, which allow for implicit operations on vectors, the code looks virtually identical with some very minor changes, and not a whole lot to do to write reasonable code here. So let's go ahead and fill in some of the gaps. Let's define a function. So here we'll make a function that's, this is two variables. So we have two functions. This would be like the f function. And so we have x0 squared plus x1 squared minus 3. And then this would be like the g function, which is 2x1 minus x0 squared. So you have two unknowns, x0 and x1, and two functions. And we return that as a vector. In this case, we return a NumPy array where the first element is function 1, f, and the second one is function 2, g. So that would be the analog with what we discussed before. Then the next function that we need to have is going to be the Jacobian function. So I'm calling it Jac, and we pass in x. And recall that the Jacobian was the derivative of f. It's a matrix, so it's going to have 4 elements for a 2 by 2 system, a 2 equation and 2 unknown system. So the first element is going to be df0 dx0. In this case, there's f0, and the derivative with respect to x0 is 2 times x0. That's what we get. The second element is going to be df0 dx1. So there's x0, and the derivative with respect to x1 is going to be also 2 times x1. And then the second row corresponds to derivatives with respect to the second function. So here we have df1 dx1. So this will be, there's df1 with respect to x1, it's just 2. So we put a 2 in. And then the final derivative is 2 times dx0, 2 times x0, the negative there. So that's as simple as it is. We just evaluate the analytic derivatives for each 4 and call that our function, and that's what we're going to return. So then we can call the Newton ND function. So we're going to define an initial guess. x0, we'll call that an array. We'll just guess 1s for both the x0 and x1. The 2 elements of the solution vector, we'll guess 1s. And then the solution and the number of iterations will be Newton ND, and we pass x0. We pass the function that we're interested in solving. We pass the derivative, the Jacobian matrix that we're interested in solving, the Jacobian function rather, that returns the matrix. And then we pass an error tolerance, in this case 1 to the minus 6. And then I'm just printing out the solution. So you can see the solution here is minus 1.4142 and 1. That's the solution. And then it's always a good idea to check to make sure that the solution was found correctly. So if we evaluate the function, if we pass the solution into our function, we should get a vector of zeros. And in fact, that's what we get, practically 0. So we feel good about that. Okay, so let's move on to something. So that's all I want to talk about with the multidimensional Newton's method. It's pretty straightforward, but there's got a lot of symbols in there, and you want to make sure that you understand each individual step. So before we finish, I just want to mention a kind of an interesting property of the Newton's method, which is a fractal. Many of you have seen fractals before. They're those pretty mathematical pictures that as you zoom in, you see more and more structure. And it can be fairly beautiful and very complicated behavior. If you consider a really simple polynomial, just like x to the 4th equals 1, and if we solve that equation for x, we put it in f of x equals 0 form. This is 1D again. X to the 4th minus 1 equals 0. So f of x would be x to the 4th minus 1. The roots are obvious. The solutions are at x equals 1 or x equals minus 1, or because it's a 4th order polynomial, there's 4 roots, and in this case 2 of them are complex. You have a root at I and at minus I. So if you were to draw the complex plane, you'd have roots at the cross, so plus 1, minus 1, I, and minus I. Now, we talked about how in Newton's method, it always starts from a given guess. So you start at some initial guess, and then you update that guess. And where you end up depends on where your initial guess is. If you guess some point in the complex plane, so for this problem, if you guess some location in the complex plane and then apply Newton's method to it, it will converge to one of those 4 points, 1, minus 1, I, minus I. And which one is converged to depends on the location of the initial guess. So here we're going to apply that. We're just going to pick a whole bunch of points, 400 times 400 points in the complex plane, and we color each of those points as follows. So each point is a starting point for Newton's method, and we apply Newton's method. I think I applied 20 iterations to this problem. We just hit this equation 20 times with Newton's method, and then we color each of those starting points based on which solution we find. So there will be 4 colors on the domain because there's 4 solutions, and every starting point goes to a different place. So there's the code. You can see it's not a very long code, and you can see the picture. So if you're in the green, any point in the picture, if you start in the green, it ended up solving it to the solution x equals 1. And it's quite amazing that the structure, you can have a lot of points. You can have points that are rather far away from the solution point. Zoom into these different regions of space there. And if you're close enough to the root, there's nothing very interesting happening. It always kind of converges there. But you get this very interesting behavior that you can zoom in and in on to see which solution it goes to. So who knew that you could get such a beautiful, complex, interesting pattern out of such a simple equation? It's quite an amazing result, and I think it's great. It's pretty easy to change the code so that if you wanted to do a different polynomial, say we did x to the 8 minus 1, we can just uncomment this guy, comment out this line, and if we run that thing, then we get another really interesting pattern where in this case there's 8 different solutions, and you'll see 8 different colors. So that's all I wanted to talk about today, and please let me know if you have questions, and any feedback is welcome. So thanks.